For months, the public was told that 3I Atlas was nothing more than a comet passing through our solar system, a cold, weakly bound ball of dust and ice melting under sunlight. Harmless, ordinary, predictable. But mainstream science has now published a paper that tears that narrative apart. This new peer-reviewed paper re-examined 15 separate observational studies, ran deep thermophysical simulations, and modeled how an interstellar object survives exposure across millions of years. And after all of that work, the conclusion is blunt and impossible to ignore. 3I Atlas does not behave like a comet. Not unusual, not unexpected, inconsistent. That is the word they chose. After months of NASA calmly repeating that 3I Atlas is simply another icy wanderer approaching the sun.
To start with, I'd like to address the rumors right at the beginning. I think it's important that we talk about that. This object is a comet. It looks and behaves like a comet and all evidence points to it being a comet. But this one came from outside the solar system, which makes it fascinating, exciting, and scientifically very important.
Their own scientific community is now publishing research that describes it as a crystallized relic containing metallic regions and signs of geological processing from a long-dead planetary system. According to the authors, only two origins remain viable: a fragment of a differentiated exomoon or a compacted, lithified piece of planetary crust. Both mechanisms are natural, but neither is compatible with the comet model agencies have been pushing since day one. If you've been tracking this object and sensing the official story didn't line up with the data, now you know why. The moment you see a mainstream astrophysics journal publish a paper titled "An Interstellar Crystal Fossil in the MIR Relic Framework for Small Body Evolution," and the very first line claims that 3I Atlas displays a rare combination of dynamical, chemical, and structural anomalies, it becomes clear something huge just shifted. This is not fringe speculation. These are researchers who spent months revisiting every available measurement, cross-checking 15 independent studies, feeding parameters into thermophysical models, and simulating endurance across deep space radiation environments. They evaluated three possible origins: a chunk from a differentiated exomoon, a lithified crust fragment from a rocky world, and the weak, ice-rich comet model NASA has repeated publicly since the object's discovery. Their results are unambiguous. The first two explanations fit the data. The comet scenario does not. After running the physics, testing survival thresholds, analyzing reflectance and composition, and matching observed behavior to formation models, the team concludes that the comet hypothesis cannot be reconciled with the observations. They state this plainly: no hedging, no cautious disclaimers. Instead, they describe 3I Atlas as a geologically processed, high-strength crystalline relic capable of enduring interstellar travel. This is the first time a mainstream academic paper has openly rejected the comet interpretation, while the object is still being monitored. And the implications are enormous. For months, officials insisted 3I Atlas followed the standard comet playbook. Solar heating triggers outgassing, sublimation pushes dust into space, jets form, the coma lights up. Simple, familiar. But every new dataset has chipped away at that explanation. Now the paper lays out, point by point, where the comet model breaks. The first major problem involves mass loss. 3I Atlas's tail spans nearly 5 million kilometers. The anti-tail, pointing directly toward the sun, extends more than 1 million kilometers, while maintaining coherence against solar wind speeds exceeding 400 kilometers per second. Calculations by Avi Loeb show that creating and sustaining these structures over 2 months would require the release of billions of tons of material. Yet Hubble measurements estimate the nucleus is far too small for that level of sublimation. A comet's ability to shed mass is limited by its surface area and temperature. 3I Atlas exceeds those limits by orders of magnitude. The numbers simply don't align. If it were a fragile cometary nucleus, it would have disintegrated long before producing these features. Then there's the rotation issue. Early measurements indicated 3I Atlas rotates roughly 16 hours. A rotating comet releasing material will produce spiral patterns as jets curve through space. Centrifugal forces twist those jets over enormous distances, and such distortions are easy to detect. Instead, 3I Atlas produces perfectly straight, unwavering jets. No curvature, no blurring, no spiral deformation at all. That should be impossible unless the object experienced dramatic rotational deceleration, which requires forces not present in normal cometary venting, or unless the mass loss mechanism operates with a degree of stability and directionality no natural comet has ever demonstrated. Comets also tend to spin up over time, as asymmetric outgassing acts like tiny thrusters, but 3I Atlas's jets show no sign of rotational acceleration. The evidence suggests either a nearly non-rotating body or a highly controlled venting process, neither of which match standard comet behavior. Brightness patterns offer another contradiction. Typical comets show uneven coma illumination, with hot and cold regions shifting as surface patches rotate. 3I Atlas displays a strikingly uniform brightness profile with no irregularities, implying a centralized or internalized source of material, rather than random sublimating pockets scattered across a porous, icy crust. Spectroscopy deepens the puzzle further. Researchers have struggled to detect the usual volatile cocktail: water vapor, carbon monoxide, methane, in expected ratios. Instead, the spectra hint at something chemically altered and mineralogically distinct, possibly influenced by processes comets never experience. Every measurement that should support the comet narrative instead introduces more inconsistencies. The authors of the paper do not mince words. The weakly lithified comet model is very difficult to reconcile with the observations. In scientific language, that means it fails. So, if 3I Atlas isn't a comet, what is it? According to the paper, only two possibilities remain compatible with all physical constraints. The first is a differentiated exomoon fragment, a piece of a moon orbiting another star. Moons undergo internal heating through radioactive decay, tidal stresses, and formation energy, which causes heavy metals to sink toward the core while lighter silicates rise. Water and volatiles accumulate in distinct layers. If such a moon were shattered by impact or gravitational forces, fragments would retain chemical fingerprints tied to their depth of origin. A portion from a metallic interior would be dense and stable, potentially containing concentrated nickel or cobalt. A piece from hydrated outer layers would show mixed silicates and water-bearing minerals. 3I Atlas could easily be a composite shard carrying traces from multiple layers. The second plausible origin is a lithified sedimentary crust fragment from a rocky exoplanet or large asteroid. Sedimentary crusts form when loose grains and minerals accumulate, compress, and harden under geological pressure. Over millions of years, these layers become rock, structured, mineralogically diverse, and far tougher than cometary ice. A fragment of such crust would show resistance to erosion, durability under intense thermal cycling, and reflectance signatures shaped by ancient environmental chemistry. Such material would explain 3I Atlas's stability, its coherent jets, and its metallic and hydrated domains. A comet cannot produce these traits, but a geologically processed crust can. Both the exomoon fragment and planetary crust fragment fit every observed constraint. Both align with the spectroscopic anomalies. Both explain the high density and extraordinary resilience. And both require a rethinking of what interstellar visitors can be. Metallic signatures are the cornerstone that breaks the comet model. Comets form in the cold outskirts of planetary systems, where metals like nickel and iron never condense into meaningful concentrations. They remain dispersed as dust or gas. Yet 3I Atlas displays clear metallic features, and more intriguingly, a nickel-to-iron ratio unlike that of any known comet or asteroid in our solar system. The paper states that such metallic and hydrated signals point to crustal geological processing, meaning the metals were concentrated through planetary differentiation
rather than random accumulation. This is precisely how planetary cores form, through heat, pressure, and gravity separating materials by density. Comets cannot undergo this evolution, but moons and planets do. If 3I Atlas is a fragment from a differentiated world, the metallic content suddenly makes perfect sense. Its density, its durability, its spectral fingerprints all align with a piece of ancient planetary architecture, a relic from deep inside a body that once possessed geological activity. The fact that 3I Atlas survived interstellar space for possibly billions of years adds another layer of intrigue. Interstellar travel is brutal. Cosmic ray bombardment, constant micro-impacts, and extreme thermal cycling. Fragile cometary bodies break apart easily under such conditions, yet 3I Atlas arrived intact. The authors describe it as a high-strength crystal relic, not in poetic metaphor, but in literal physical terms. Whatever this object is, it was forged to withstand extraordinary stress and unimaginable time spans. Meanwhile, official agencies continue to describe 3I Atlas as a comet. NASA's public updates cling to the standard language. ESA focuses on orbital mechanics, avoiding mention of composition. Yet the new paper, written by researchers operating within the same scientific ecosystem, states directly that the comet hypothesis fails. The disconnect is glaring. Some of it is institutional caution. Agencies rarely issue bold reclassifications until consensus settles. But another part seems like reluctance, hesitation to acknowledge what this object implies. For decades, interstellar visitors were placed into two boxes: comets or asteroids, leftovers from planetary formation scattered into the void. 3I Atlas doesn't fit. It is chemically unusual, structurally robust, and geologically processed in ways that demand a new category entirely. The paper suggests that the James Webb Space Telescope could determine whether 3I Atlas is a moon fragment or crustal material based on targeted spectroscopic signatures, but no such observations have been announced. The data remains incomplete, the agencies remain silent, and the gap between what researchers are discovering and what the public is being told is widening.
The paper's final statement may be the most consequential. It argues that current categories, comet, asteroid, dwarf planet, are insufficient to classify objects like 3I Atlas. It proposes a new branch of classification for small interstellar bodies based on measurable physical properties. That implies this object is the first confirmed example of a class we didn't know existed. A geological artifact drifting between stars, carrying information about ancient planetary systems, arriving at our doorstep with a story carved into its structure. And that raises a profound question. If 3I Atlas is not a comet, if it carries the mineralogical fingerprints of an ancient world, then what else has been passing through our solar system under the wrong label? How many fragments from shattered moons or extinct planets drift silently in the interstellar dark? How many relics have we misclassified because they didn't fit our old frameworks? 3I Atlas doesn't answer these questions, it creates them. And that is what makes this discovery so important. We're not just witnessing an unusual visitor, we're watching the birth of an entirely new understanding of what travels between the stars.